Uh, Hello, this is Lichen. In this video, I'm going to briefly introduce my project in in the course computational photography. And the title is Fast and Usable Gradient Domain Processing with the Heterogeneous Parallelism in CUDA. Um, so firstly, the introduction. So during my previous assignment, I have noticed that the Python NumPy, the Python NumPy implementation of the iterative uh, gradient domain processing uh, image integration can be quite slow, uh, although the implementation is straightforward. And yeah, and and actually the iterative algorithm is quite slow since he's put he's pushing quite heavy pressure on the CPU and the memory bandwidth. So if we turn to some of the heterogeneous the heterogeneous parallel architecture, such as the GPU in the CUDA programming, uh, yeah, it's going to be more suitable for the image editing tasks. So there's going to be a significant performance gain. It's going to be much faster, but actually, most of the GPU code, including CUDA, are quite low level and not easy to be understood by the normal users. So it's not easy to use. So how to make the things both fast and easy to use. So in this project, I I implemented the critical logic of the gradient domain processing algorithm as a GPU core, uh, but but also a Python wrapper layer based on that GPU core to expose simple simple open API for uh, for the users according to specific application needs. So for the CUDA backend, basically in the CUDA implementation, I mainly break it down into two separate parts. For the gradient fusion, I make this part extendable. So yes, so the gradient fusion model can choose to use different logic for different objectives. And for the conjugate gradient descent part, the most challenging part would be how to handle the dot product. It's going to be an all reduction. So to optimize this performance, I have uh, I have implemented it as a tree-based reduction to to reduce the steps and the contention in the contention on memory addresses to log scale. And for the Python wrapper, so suppose for the CUDA backend, it's always going to be handling a pair of equal-sized images, but uh, for for the Python wrapper, I can translate more complex requests from the users. So for example, if I want to handle a sequence of images or a video, yeah, the wrapper is going to automatically invoke multiple times of the CUDA backend and merge the results together. Uh, so firstly, I have an evaluation of the performance of the CUDA backend compared to some parallel framework in CPU, and of course the Python NumPy implementation itself, and yeah, that shows a very significant speed up increase and quite satisfactory for the real time application and interactive purposes. And so here is a video patching demo. I have a small patch of sun, and I want to patch it to every frame in this video on the blue sky, where I choose 10 seconds. So it's going to be 300 frames in total with 30 FPS. So we can run it immediately. So those are the wrapper part. And with that wrapper API, I can do all the things with only one line of Python invocation. Yes. So as we can see, the program is proceeding quite fast. Yeah, it's very fast for each frame since it's invoking the CUDA backend, and it's take the benefit from the heterogeneous parallelism. Yeah. So at the end of the execution, the program automatically reports the total time and the processing FPS. So it's quite fast, and we can also get the output in the designated path. Okay, let's take a look. Yeah, so as you can see, the sun is seamlessly patched into every frame in the video. Yeah, and that matches our purpose on doing the post-zone patching into the video. And here, yeah. So based on the preliminary results, here are some future works, such as the first optimization in the low-level CUDA level, and use pipe or shared memory to reduce to reduce the disk I/O as the intermediate results, and also to help users to write their own to write their own CUDA gradient fusion code. Yeah. So that's all my project is about. Thanks so much.